Okay, how's everyone feeling today? Okay, yesterday we had a lesson on the two main factors that affect how much current is running through a wire. How much current is running through a conductor. Yes? And basically, the current was directly proportional to one thing, and it was indirectly proportional to another. What was it directly proportional to? Claire?
Voltage.
The voltage. And what was it indirectly proportional to? Swathi?
1 over R. Resistance.
1 over the resistance. And if you put those two together, you get the formula for Ohm's law, which is I equals V over R. That was yesterday's lesson. If the wire is connected to a greater difference in charge concentration, known as a greater potential difference, greater voltage, you'll have a bigger current. However, if the wire itself has a greater resistance, you'll have a smaller current. Today's lesson, we're going to focus in on the resistance of the wire. And what physical characteristics of the resistance of the wire, gives it a lot of resistance or a small amount of resistance. So today's lesson is about the resistance of the wire and what characteristics of the wire have an effect on its overall resistance. So the overall resistance of the wire, how much opposition, how many ohms, depends on three things. R equals rho, not for density this time, represents something else. Rho L over A. Three factors. L stands for the length of the wire. If you have a longer wire, that wire will have more resistance. The longer the wire, the more the charge has to make its way through, having more and more collisions with the atoms on its way. The longer the wire, the greater the overall resistance of the wire. So that L is the length of the wire. The A stands for the cross-sectional area of the wire. This area right here. If you have a wire that has a bigger cross-sectional area, that means it's like fatter, it's wider. It's kind of like a bigger pipe. A bigger pipe can easily move more water through it. Well, a thicker wire can more easily move charge through it. I like to think of it like as a superhighway. And the more lanes that a superhighway has, the wider it is, the less resistance it has. It's much, much easier to get massive amounts of cars through. So L is for the length of the wire, A is for the cross-sectional area, And rho represents the material. It's like a coefficient. Rho is like a material number, and every metal has its own rho value. I personally call rho the material number. Copper has its rho value. Gold has a rho value. And if you multiply the material number, bless you, times the length divided by the cross-sectional area, you get the overall resistance which is what we're interested in. Once you have the overall resistance of the wire, then you could use that resistance back in Ohm's law formula to calculate the current or the voltage, depending on what the given is. So what we're really concerned with is the overall resistance. So let's take a look at units now. What most likely is the unit for the length? Alex, for the length of the wire, that's probably in meters. What about the cross-sectional area, Brett?
Meters squared.
Like how you're thinking. And when we multiply it by that material number, we want the resistance to come out in ohms. So take a moment to look at the equation and try to determine what do the units for that material number, what do the units for the material number have to be? So that everything jives out. So that the units on the right multiply out and you're left with the ohms on the left. Tommy. No. I just want to use what we see is what we get. You're jumping, making it too complicated. Just using the units we have present on the board there. Ohms times meters. That material number is given in ohm meters. You'll have to use that tonight when you do your homework.
That was the Slinsky. That's how I'm naming all the Slinsky.
Notice meters divided by meters squared, you're going to have a meter in the denominator, and that's going to cancel out with this meter, and then you're left with ohms. You see now, Tom?
Yeah.
So I held off on actually telling you the name of the material number because I want you to think of it as the material number. Because a lot of times students get the material number mixed up with the big capital R, the resistance, and that's what we want. We want big capital R. We want to know the overall resistance of the wire in ohms. Little rho, that's just the material number. However, its name is like so close to big R that it gets a little bit confusing. Big R is what we're trying to calculate. That's the overall resistance. But the official name of the material number, Alex, what's going on? You're misbehaving somehow. Okay. You're scratching your head?
It's Brianna.
Brianna.
Do we need to move
Nah.
here again?
Okay. The official name of the material number is the resistivity of that material. So there's resistance, which is like the overall opposition to the charge flow, and then there's resistivity. That's just a number that represents the type of material being used. So let's look at a sample problem. Let's say we have 4 wires made up of the same material. If these 4 wires were made up of the same material, you would be able to tell me which of the 4 wires has the greatest overall resistance and which of these 4 wires would have the smallest resistance. Take you a moment, identify that yourself. Think of the formula. R equals rho times L over A. And since all 4 wires, I'm telling you, have the same material, we know they all have the same resistivity. So you have to look at their L's and their A. Swathi, if you wanted to have the biggest resistance, what do you want the L to be? Big or small? Big. You want the L to be big, because if that's big, then the R will crunch out big. Okay, so you want the longest wire. Now, what about the cross-sectional area? You want that to be really small, okay? And if that's really small, then you'll get a really big resistance, yes? So which of these wires has the most resistance? Which one has the biggest L and the smallest A? The first one. On the other hand, which one would have the least amount of resistance? Simrit, would you want the wire to be long or short for the least amount of resistance? Short. You want the L to be small so that the R is small. But what about the cross-sectional area? You want that to be big. So which one is short but yet big cross-sectional area? The last one. This one here, this wire would have the least resistance. Now there's one more factor that's not shown in this formula, and that factor is the temperature of the wire. The overall resistance is directly proportional to the temperature of the wire. If the wire heats up, the inside atoms are going to have more jostling, more kinetic energy, and it's going to be harder for the charge to move through that craziness. Usually, at this stage of the game, you just need to know this fact here, and you need to know that the resistance equals the resistivity times L over A. The truth of the matter is, it's a little bit more complicated, okay? This is basically where we're going to keep it at, above that line. But the truth of the matter is, this resistivity number that's really a function of the temperature. So basically, it's really something like this. The overall resistance is equal to the resistivity, which is a function of temperature. You know how like there's x and then there's f of x? Well, the resistivity, which is a function of temperature, times the L over the A. And then it's a more complicated formula for that function. So it turns out that the resistivity actually changes depending on the temperature. And usually you're given the resistivity at room temperature. But you need to know that like if the temperature goes up, then the resistivity would go up and the overall resistance of the wire would increase. So basically, the resistivity at like a different temperature other than room temperature would equal the original resistivity at room temperature times bracket 1 plus alpha, which is another number, what's that called? The temperature coefficient of resistivity, alpha, the temperature coefficient of resistivity, times, parentheses, the new temperature minus TO, which is usually room temperature. But like I said, what you need to know, this formula here, and that usually the higher the temperature, that's just another factor. One last example I want to show you with the resistance and this equation. It's a popular question. Let's say you have a wire that has a certain radius, and let's say its radius is R. And then let's say you have an identical wire and let's say its radius is twice as big, 2R. And let's assume that the length of these two wires are the same length, and let's assume that it's the same material. So how would the overall resistance of the lower wire compare to the upper wire? Is it going to be more or less? Let's start there. What do you think, David? Is it going to be more or less? Is the lower one going to be more or less?
Resistance?
Yeah.
Resistance.
Huh?
Less resistance.
It would have less resistance because it's fatter, yes? The question is, how much fatter? And if you look at the formula, you have R equals the resistivity times L over A. And they're both the same material, so the resistivity stayed constant. They're both the same length, so that stayed constant. And at first, you might think, incorrectly, that the lower wire is double the cross-sectional area. Therefore, it's going to have half the overall resistance. But what's the deal, Paulie?
You gotta square it.
Yes, why?
It's a circle. Oh, yeah. And it's area is pi squared.
Yes. The area is equal to pi r squared. So if you double the r, what happens to the area, Jacob? You double the r.
4R squared.
Yeah. So how's the new area going to compare to the old area? No. If you double the radius, how is this area right here going to compare to this one here?
Like 4 times as great.
Yeah, this one here is going to be 4 times as great. So now if you come over here, if the area is 4 times as great, oh, maybe you were jumping the gun. I was just talking area right now. Then what happens to the overall resistance? It's 1/4, and that's what you're talking? Yeah, the overall resistance would be 1/4. So if this has a resistance R1, R2 would be 1/4 times R1. Oh, this is tricky though. because over here it's resistances, and over there these are radii. Sorry about that. These over here are resistances. These over here represent the radius. This leads us to our next topic, which is electrical power. We have already learned about power and how to calculate power. Power is equal to work divided by time. Sometimes the question will just blatantly ask how much power is needed. Or another way of asking the same exact thing, the question could ask, what is the rate at which the work is done? What we're going to look at now is how to calculate power when dealing with an electric circuit. So I'm going to go back to that scenario where I have two metal spheres, and let's say this one is positively charged, and let's say this one is negatively charged, and I'm going to connect a wire from the positive through a light bulb to the negative, and the conventional current, the positive charge flow, is going to flow this way through the light bulb over to here. And if I want to keep this current going, I need to maintain the difference in charge concentration. I need to maintain a potential difference. So basically, as fast as that positive charge comes over here, I'm going to have to take that positive charge and push it back over there with my EMF. And that takes work, because it's not easy to keep putting those positive charges back. Oh my goodness. Oh, I got to keep putting them back just as fast as they naturally go over and go through the light bulb. So EMF, remember, that's just a voltage source. And remember, voltage is just the work done per charge. So it's obvious that work is being done to put that positive charge back. And if we wanted to calculate the rate at which that work is done, we'll be calculating power. So, electrical formula for calculating power. Watch as I razzle-dazzle you with my derivation. Power is equal to work divided by time. But we know that voltage is equal to work done per charge. If I rearrange this, work is going to equal the voltage times how much charge is moved. I can make that substitution over here for W, and I get power equals voltage times charge over time. Finally, I can algebraically rewrite that. Power equals voltage times charge over time. Anyone recognize that last line there? There's something that should stand out. See one hand, don't shout it out. Anyone else see it? Something that should be kind of like shouting out at you. That last line there. What is it, Tommy?
You can substitute for T2.
Yeah. Charge per time. That's how fast the current's flowing. That's the rate of current. That's the rate of charge flow. So, voila, we have our new electrical power formula. It's simply the voltage times the current. sometimes you're still going to have to use the old school formula from mechanics. Power equals work over time. But more likely, when dealing with electric circuits, you're going to use this new handy-dandy formula. The power just equals the voltage times the current. Let's go back to our little diagram here. Let's pretend that our EMF, our voltage, between here and here, let's pretend that that's a 12-volt EMF. And let's say that the current going through the wire, through the light bulb, is 2 amperes. You may ask, hey, what's the power rating of that circuit? Or same question, what's the rate at which the work is being done? No problem. P equals V times I. P equals, it's going to be 12 volts times 2 amperes. P equals 24 volts times amperes. And you probably wouldn't write that out. It's going to end up being watts, but let's take a closer look at this. Again, you probably wouldn't write all these steps, but I just want to do it for education's sake. 24, a volt is a joule per coulomb. How many joules of energy for each coulomb? And an ampere is a coulomb per second. How many coulombs are going through the wire each second? And notice what ends up canceling out there. Swazi? Coulombs. Excellent. So you're left with 24 joules per second. And those are great units of power because they're like self-explanatory. You're doing 24 joules of work each second to keep this sucker going. But to honor another scientist, we've seen this before. A joule per second is called a watt, for James Watt. Now, we have a new power formula, V times I, and then we have our good friend Ohm's law. I equals V over R. The current going through the wire depends on the voltage and the resistance. Well, those two formulas can give us other versions of the power formula. Sometimes students like to memorize all the different versions. I myself, I just always use these two things right here. But maybe someone could step up and combine these two and give me another version, another power formula if you combine those. Can anyone give me another version? Mike?
Power equals I squared times.
That's another one. And does anyone see the third one? Gary? That's what I'm saying. And I saw that hand up. Brianna, good job. V squared over R. So here you have 3 power formulas. That gives you a lot of power to choose. That was a Slinsky.
That was a Slinsky.
What?
Slinsky.
Oh, Slinsky?
Yeah, we're shorted so we can just roll off the top.
Slinsky.
So just got Slinsky.
Ladies and gentlemen, sometimes you might not be asked to calculate the power or the rate at which work is done. Sometimes you might just be asked to calculate the work done or the energy used. So let's make a note. There's a distinction. Power is equal to the rate at which work is done. So both the left side and the right side, two different ways of asking the same thing. But sometimes you're asked simply, how much work was done? And that's equal to how much energy was used. So there's basically two questions here. What was the power? And what was the work done? But there's just other ways of asking those two questions. So let's focus on this, calculating the work done. Well, we start off with our power formula, work over time, and we'll take a break and come on back and talk more about that.
Come on.
To calculate the work done, you can just rearrange the good old classical power equals work over time, and you get work equals power times time. Solve for work, bam. Now you know how much energy was used or how much work was done. Too easy. Now once again, people like to combine things and whip things up. And since we had three formulas for power, this work formula could be rewritten three more ways. If you're that kind of person. Can anyone give me another version of the work formula? Dorothy! VIT. You know me. It's like a rap. Come on. It's like a jungle. Sometimes I really wonder. VIT. Another version of the work formula. Come on, people. We have to do some work. Dorothy. I squared times R times T. Dorothy, bring it on home. Last one. That's what I'm talking about. You want to memorize all those formulas? Great, fantastic. Okay, but you really just kind of combining different things. So, let's take another look at units, shall we? If you have work equals power times time, usually we use units like this. 1 watt times 1 second. And then you could rewrite this. You could say 1 joule per second times 1 second. And then the seconds cancel out. And you're left with good old what? What do we have left there? 1 joule. And the work done is in joules. Basically, that's what we're going to be using. Okay? However, sometimes you're asked questions about another version, and it's the type of unit that's used on your parents' electrical bill. When they get their bill from LIPA, okay? It doesn't say how many joules of energy was used. It has a different unit, and basically we come back over here, and instead of just using watts, that's too small. So they use a bigger unit which is a kilowatt. Okay? A kilowatt, that's 1,000 watts. And then instead of using seconds for time, the time is measured in hours. And then if you multiply this out, you get 1 kilowatt hour. Now a joule is not equal to a kilowatt hour. You know, kilowatt hour, that's a much larger unit of energy. And I think it might be one of your homework assignments to figure out that conversion. Okay?
Wait, 1,000 joules is 1 kilowatt?
No, it's going to be more complicated than that because of the hours. All right, what the heck? Let's quickly look at that. You know, W equals P times T. So we have one. Or here we have like 1 kilowatt hour. Yes, and 1 kilowatt hour is equal to 1 kilowatt times 1 hour. Yes, and what's a kilowatt? 1,000 watts. And what's an hour? 3,600. 3,600.
60 times.
60 times 60.
Well, we count it out. 1.
No.
How many seconds an hour? 3,600.
5.
So basically, it's going to be 1,000 joules per second times 3,600 seconds. And what do we get? 3,600,123 joules. 3,600,000 joules. So 1 kilowatt hour is 3,600,000 joules. You heard it here first. Okay? Okay, in closing, power is equal to work divided by time, but when you're calculating electrical power, a very convenient formula to use is voltage times current. From those two formulas, and if you mix in Ohm's law, you could whip up a whole slew of formulas. But basically, those are the main three.